Okay, good afternoon, everyone. Welcome to our panel session for the hardware testing and the model quality assessment and validation. My name is Jing Wang. I'm a principal engineer from NLR. I will be hosting this panel. So for this morning, you have heard a lot about data center load modeling, and this session is again about modeling, and especially for the model quality assessment. And the presentation will be, I think, be more technical, and we have a group of experts to share their experience in this field. We have two utilities and the national lab. We have also a few consultancy companies to share their experience regarding the model validation based on their experience. That covers hardware testing, covers laboratory controller hardware in the loop testing, and also EMT simulation. So this panel, we will have five presentations, and each speaker will have 15 minutes. So I'm going to start to introduce our first speaker, Pauli Partinen. He's a manager from Fingrid. He leads the Fingrid modeling unit, whose work focuses on EMT and RMS simulation models, model requirements, and the model quality assessment in grid connection process. He will share his experience on the perspective on data center modeling requirement and model quality. So since he cannot make the presentation in person, and he will present virtually. Let's welcome Pauli to share his presentation. Yeah. Pauli, please take it away.
Yes, thank you very much. Let me get the screen sharing started. Let me know when you see something.
Yes, it looks good. You can go ahead. Yeah.
Okay, great. So hello, my name is Pauli Partinen, and as said, I work as manager in Fingrid's grid models unit. And little about Fingrid. We are the transmission system operator of Finland, and my unit is responsible for the ODMS, PSSC, and PS guide modeling and the customer model requirements. And in this process, we also analyze the plant compliance and customer model quality. And today I will discuss the data center model requirements and the model quality from a TSO perspective. The contents of this presentation include first a general introduction to Fingrid, and then I discuss three main questions. First, how to get the models. Second, what to model. And third, how to make sure the models work correctly. First, here is one corporate slide about us. Our organization includes the transmission planning, ownership, the operation, and electricity markets in Finland. And some numbers, we have 14,900 kilometers of transmission lines, and we are only 600 employees, and yearly we transmit 76 terawatt hours of electricity, and our load varies from 6 to 16 gigawatts. So it's a rather small system, but quite widely spread. We own and operate the main grid, which includes only the meshed network, 400 kV and 110 kV. Large customers connect directly to us, and we are also connected to around 70 distribution system operators. So this was the basic corporate things about Fingrid, and then to the real topic. recently, we have seen a large number of connection inquiries. In 2024 and 25 combined, we have had 54 gigawatts of new connection inquiries for demand, which is a quite large amount for a small system like us. And you can see that the generation inquiries are also very high, but they need more demand in order to be successful as an investment. And of course, these connection inquiries usually show very high numbers because the majority of the projects are in very early phase without investment decisions. To tackle this issue, we conduct these kind of scenario studies, and in our scenarios, we see an 18 to 66% increase in industry and data center load in 5 years, and from 16 to 153% increase in the industry and data center load. And basically, this is coming mostly from data centers. Then the real question, first, how to get models. So we currently have this demand grid code from 2018 in force. For demand connections, we do not normally receive any kind of simulation models. However, we have this small text here stating that we can require a simulation model if the demand facility includes nonlinear or uneven loads. And this is, of course, the case with the data center. So this March, we announced PSSC and PSCAD modeling instructions. And even if it's a modeling instructions, it's actually a model requirements. And I will present the main ideas of these requirements. And in addition to these new modeling instructions, we have released our new grid code for demand for public hearing. And this will introduce significant changes for the technical requirements for demand plans. This will include low voltage ride-through capability, over voltage ride-through capability, phase jump performance, for example, active power oscillation limits for the subsynchronous band, post-fault active power recovery limit. And actually, at the same time that we introduced this new grid code draft last week, we released the technical requirements for our existing grid code. And what this means is that all demand connections that will come directly to our grid will now have additional requirements that are already in force immediately from last Friday. And if this concerns all projects that don't have the main components already ordered. This was surely not a pleasant Friday surprise for our connectees, but it is a very needed one for us. And since we did that, I wanted to make this, also take this one slide from last Friday. I won't go through this, but these are the requirements that we are now implying for our connectees. And it is based on what kind of nominal active power you have in your demand connection. And for example, for a demand facility over 30 megawatt, like a data center, electric boiler, what will be required is do not disconnect in fault ride-through, and the post-fault active power recovery must be below 1 second. Ability to limit active power consumption from a signal at least 30%. Do not oscillate. Controllability. Readiness to take an external control request from controller. Then visibility, the continuous measurements, simulation models, specific study requirements. We can still imply new additional requirements if seen. And these provide flexibility for the planning and connection. And these are basically now in force for all new large demand connections connecting to Fingrid network. Then one of the issues in the data center model delivery is the ramp-up phase of the plant. What should be modeled in the first phase, and how the models develop for the ramp-up period. Here is our solution to the problem. So the first model of the plant shall be delivered to us 6 months prior to the interim operational notice, ION, which means that after that, the demand plant can start the kind of normal consumption. The model goes through a model validation, where we check that everything is correctly modeled. In the first model, the full demand plant up to the nominal power shall be modeled, but only the first block shall be online, basically. And the plant can raise the active power level to 30 megawatts before we accept the first model. And when we accept the model, the plant can raise additional 30 megawatts of the power. And then we need another model, which in turn will be accepted if everything is okay. And this goes in 30 megawatt blocks before the nominal power is achieved. And during this ramp-up period, the model shall always have online what is according to the ramp-up schedule. And for the full model version 2.0, once that is accepted, we can grant the final operational notice, FON, and normal operation of the plant can then proceed. Then what to model? We do not have any very deep expertise in the specifically data center modeling and data center architecture, but we do know what we need to study and how to build a good EMT model and PSSC model. So we have decided that the connectee shall propose how the model aggregation is done. The connectee shall also describe the functional description, meaning how the plant will behave in normal operation and outside the normal conditions, basically meaning any kind of fault condition. And this is interesting how the load sharing and parallel production is done. For example, if whether the parallel data center active power will ramp up every time there is a fault in another data center in Finland. So if they have some kind of connection so that the load will be shared to another data center inside one area in case of outage. Models are used in a very large variety of system studies, so our main focus is how everything behaves from the connection point of view. This slide presents key topics from the PSCAD requirements. We expect the model to behave correctly in all scenarios seen from the connection point. We are not that interested in what happens in, for example, internal faults. For PSCAD, it is very important to model all elements that could cause interactions with the system components and devices. And what we see that the time frame of interest is 1 minute simulation. If there is some kind of control logic that is turning on after 1 minute, it can be neglected. And the converter models must be average value models in order to accelerate the performance of the simulations, since we have a large-scale EMT model, which includes hundreds of vendor-specific models. And all UPS systems must be represented with vendor-specific models with actual hardware code. For the PSSC, the approach is a bit different. We also expect that the basic steady state and dynamic behavior of the plant is represented, but we do not require vendor-specific models, at least at the moment, because what we see that the modeling in PSSC side is not there yet. You can use PSSC library models, but special attention must be given to modeling of undervoltage write-through and post-fault active power recovery. Then to my third and last question, how to make sure models work. Our approach is not very strict. The Connect team must be able to present some kind of an existing certificate or document for any individual active unit. This means UPS systems, BFDs, StatComs, BESS, everything. If it's not available, then the Connect team shall agree testing specifications with us. And the intention is to conduct factory tests, and then the PSCAD model is validated against the test results. Then the PSSC model can be validated against the test results or the PSCAD model. This is something that we also are formulating at the moment, this necessary test list for model validation. And this was basically everything I had to present. We do not have much expertise, or we haven't had any working full models for data centers, but we are looking very much forward to continue with the discussions with the manufacturers and the connectees.
Thanks, Pauli, for the very informational presentation to share your perspective of the modeling requirement, including where to get the model, what to model, and also how to make the model work. That's a lot of useful information. Yeah, thank you again. Now I'm going to introduce our next speaker. We actually have two speakers, Robb, Wallen, and Shahil. Robb Wallen and Shahil Shah from NLR. They were talking about the data center load testing using the hardware setup from Flatiron's campus. So this is the hardware testing results, which is a different angle from the first presentation. And Robb is the key personnel at NREA for the hardware configuration and the test. Shahil is expert for the stability using the impedance scan. So now let's welcome them to give the talk. I think Robb will go first. Yeah.
Good afternoon, everyone. Robb Wallen from NLR, as Jing announced. So we're talking about our Megawatt-Scale hardware testing, a platform for evaluating the grid side and load side performance of these large loads. I'll start off talking about the hardware setup. Shahil's going to talk about the testing. The hardware setup involves our 2 grid simulators, medium voltage impedance network. We'll talk a little bit about our medium voltage data acquisition system, which is really key for this work. And we'll also show, we'll go through our control room a little bit too, as that's a new addition to our setup at Flatiron's campus. Shahil will talk about our AI load profile emulation and the voltage ride-through testing we've done, and also the frequency domain impedance scans for looking at stability analysis and also model validation. So the grid integration testbed at Flatiron's campus, slightly different picture from what you saw from Raleigh this morning. This site is about 300 acres. It's south of Boulder. Originally started out as a wind test facility. It's very windy out there. It's a very good place to beat up wind turbines. So we developed a lot of our test capability initially with kind of the wind turbine, wind systems perspective. So we had grid scale wind turbines, still have a couple. We also developed drivetrain test facilities. We have 2 dynamometers, 2.5 megawatt and 5 megawatt. And we actually developed our first grid simulator, more or less to support the voltage ride-through testing of wind turbine systems. Over the years, we saw the value of adding these additional IBRs and the value of testing them with the grid simulator. So we've had batteries, we've got a hydrogen fuel cell and electrolyzer system. We've got the original 7 MVA grid simulator. We added the 20 MVA grid simulator. And we also have a 2.5 megawatt or MVA synchronous machine. So we use that to emulate or actually act as a synchronous condenser. And we can emulate conventional generation systems such as gas turbines and steam turbines with that. Kind of an overall schematic view of the site shows how everything's interconnected. So one of the really big values of our site out of Flatirons campus is we have all of these megawatt scale assets kind of distribute across the whole site, and we can interconnect them to each other or to the 2 grid simulators or to the utility. So we've got a 20 MVA substation with 115 kV feed from Excel. It says 20 MVA. We're limited to 20 MVA of export through that substation, but we can pull up to 50 just because of the interconnection agreement. But so we have the Excel bus, and then we also have multiple what we call CGI buses that allow us to, on a separate medium voltage distribution system, interconnect these assets. You can see the 2 grid simulators down there at the bottom. Probably kind of a unique thing about our site is that not only we have all these assets, we have multi-megawatt grid simulators, but we have the ability to connect, an asset between 2 grid simulators. So it's perfect for doing this, double conversion UPS validation. And the interesting thing too is that we've moved from doing, you can see this is basically all generation to pivoting to load. So we just kind of extended this bus down, plugged in some of these UPS, AI data center UPS systems, and we've been working on validating that. And Shahil will talk a little bit more about that. Just a few notes on grid simulators, a little bit more detail. I won't go through all the specs, but our first grid simulator we commissioned back in 2013, 7 MVA. It's back-to-back AC, DC, DC, AC conversion, outputs of 13.2 kV. It's can support up to 40 MVA for short periods of time, which is good for testing these like doubly fed induction generators and things like that have high fault currents. It has a 1 millisecond response time, so it's pretty quick. We have full interfaces for this, so we can either operate it open loop and run fault profiles, voltage faults, phase jumps, frequency events, or we can plug it into a PHIL power hardware in the loop system and run more sophisticated setups like power system emulation or impedance emulation. Also, obviously, it has range frequency. We can go, 45 to 65 hertz is what's on here, but we can actually go well beyond that. So we've actually used it for 50 hertz validation as well. Our second grid simulator, CGI2, controllable grid interface, we added about 2 years ago. So 20 MVA system, or we commissioned it maybe 3 years ago. So changes from CGI1, we added 34.5 kV tap to our transformer, to the output transformer. So we can do 13.2 kV and also 34.5. And we can go, I think, 50% over that. So we can go up to about 50 kV on the high side. It's faster, 100 microsecond response time. And we also added, as part of the build, we did a up to 5,000 volt, 4,000 amp bidirectional DC power supply. So good application. We're hoping to use it for some of these newer, possibly 800 volt data center power systems. I think there's much more. Yeah, voltage quality is really good on these. We have output filters that, keep our voltage THD below 1%, no load. Another kind of unique piece of equipment we have is our medium voltage impedance network. So we can emulate impedance with the CGIs, but if we want real impedance or to validate our impedance emulation, we can insert this piece of equipment into the circuit, and it allows us to reproduce a SCR down to 1 for percent of MVA article or 7 MVA test articles. It also has series compensation capacitors built in, so we can do series compensation circuits as well. A couple notes about where we run this whole thing from. This is from our new control center facility. We finished this in 2025. So this houses all of our a good chunk of our real-time compute assets. So those are the Opal RTs and Typhoons, and also the CGI digital twins. We have a digital twin of the CGIs that we can use to pre-run experiments. We run an SCL, RTAC, SCADA screen for that, so we can see what's going on across the site. We also stream all of our data into a time series database, so we can go back and pull up different events. And we've automated most of this system with basically MATLAB. So we can synchronize our CGIs for event generation. We can synchronize test article control, data collection, post-processing. So we have a pretty small team doing a lot of testing pretty efficiently. So we have, for data acquisition, we have PMUs and obviously all the SCL equipment. We also have our medium voltage data acquisition system. So this is a system built in-house by NREL. It's a distributed network of GPS synchronized 24-bit 50 kilohertz voltage and current measurements. So we have about 40 of these nodes running all across our site, and we can pick which nodes we want and we can trigger them, and then they'll store locally, and then we can pull the data back with our scripting and then realign it and post-process it. A couple of pictures up here. One, and then also we have a client for that system that allows us to kind of use it as like a virtual oscilloscope. So across our whole site, we can pick like 2 voltages that are all way apart, and we can pull them together and watch them in real time to look at like voltage waveforms and process data. I included a picture of some of the sensing side of that. It's pretty flexible. We can use PTs, CTs, or in this case, this is our main measurement off of CGI 2, and these are some high precision voltage dividers rated for I think 20 kV, and some LEM current sensors, and a picture of one of our boxes. I think that is about it from my side. I'll queue up.
Thank you, Rob, for giving that overview of our testing capabilities and measurements that we do at the Flatirons campus. I'll now walk through some test examples, particularly related to large loads and data centers, and how we use it for testing the performance of data center power supply equipment, and also for model validation or model quality check. So the first unique test that is required for data center power supply equipment is emulating AI load profile. And what you see here is we use one of our grid simulators to act as a load. Instead of grid emulator, it basically became load emulator, and basically it can act as a load, data center load, where it can emulate any AI load profile that we feed into it. On the top, what you see is the orange one is a reference, and then the blue one is the actual measurement. So the CGI or the grid simulator is consuming this power in real time, and then it is, for this particular test, it was supplied by a 2.2 MVA inverter. So basically we are exposing the 2.2 MVA inverter to an AI load profile. And then at the bottom you see high resolution measurements showing 3-phase voltages, 3-phase currents during one of the particular steps of AI load fluctuation. And in terms of the ramp rate, we can go from 0 to full power within few milliseconds. We can go around 0 to full power of several megawatts within 4 or 5 milliseconds. If we want to go faster, we need to, of course, tune our grid simulator, but that might result in some control interaction. So that basically I'm trying to say that that requires additional tuning, but it's still possible. But in any case, this ramp rate of going from 0 to full power within 4 or 5 milliseconds is much more than what you need for data centers. And that makes us basically a good place to test data center power supply equipment. Of course, we can also do the traditional tests like low voltage write-through and impedance scans to test the compliance with various voltage write-through standards, as well as use it for testing the model quality, validation of the model. So on the left, you see a test we ran on, I think, a 2.x MVA PV inverter for voltage dip test, where we reduce the PUI or the interconnection voltage by 60% for 50 milliseconds. And then the response here compares the actual measurements with the PSCAD model. So it not only serves as testing the compliance with the write-through performance, but also for model validation. And on the right is impedance scan, where we are looking at the D-axis admittance of an inverter, and then comparing response between PSCAD model and the actual hardware. We had to go through several iterations on improving the model quality. So here you are seeing textbook type response or matching between model and the actual hardware. But of course, initially the model had some issues that we had to figure out and work with the vendor to address that. So I'll conclude my presentation with this project that we have been working on with On Energy of testing a medium voltage multi-megawatt UPS for data center applications. Instead of the low voltage UPS that are traditionally used that I talked about earlier today. This is a medium voltage UPS, sits slightly closer to grid POI, but more importantly, it uses a long duration battery energy storage, and then two inverters, two back-to-back inverters. Having two grid simulators that we have at the lab and all these testing capabilities like AI load profile emulations, impedance scans, voltage jump, makes us like a good fit for testing such equipment where we need two grid simulator approach, one for emulating load transients and one for emulating grid disturbances like low voltage, and that to do it simultaneously. And at the bottom, you see one branch of this UPS, basically battery and two converters. Right now, we are actually testing three branches. So we started with testing one branch of UPS, and now we are testing, going to start testing with three branches of UPS in parallel. So this is my last slide where I want to talk about testing the grid side and load side performance of this AI UPS simultaneously. At the top is the voltages, and at the bottom is the active power. The orange measurements, they are on the load side, and the green ones are on the grid side. The main, and Mike from On Energy will talk about more about this UPS later today, but the main goal of this UPS is to use battery energy storage to isolate load disturbances from the grid. So grid doesn't see any AI load fluctuations or load crash, and then the load doesn't see any disturbance on the grid. If there is a low voltage blip on the grid, the load voltage remains constant, and that can be demonstrated using some of these measurements here. So starting with here, so we are running a particular AI load profile, and as you can see on the load side, we are feeding that load, but on the grid side, the power remains flat. So there is the AI load fluctuations don't transition to the grid side. And of course, there is a change in the power that we draw from the grid to make sure that we are meeting the load demand, but the ramp rates are limited based on the requirements set by the grid operator. The second load disturbance is here where the load suddenly goes to basically zero. So it's an AI load crash. That can happen because of some failure in the equipment. It can also happen if all these data centers, they are operating on a synchronized algorithm. So if algorithm crashes, the demand can also crash. And again, the grid side power doesn't crash at the same instant, but basically the grid power is ramped down in a manner such that the grid doesn't see this big disturbance. And then here, this 4 and 5, they represent some grid voltage disturbances, low voltage right through, both low voltage and high voltage. And the second event, the number 5, it's actually a very severe 100% voltage dip event. And again, we are seeing that the the UPS is able to bring back the grid demand in a very short duration, and at the same time, load doesn't see this disturbance. So with that, I would like to conclude that the technologies for power delivery in data centers are evolving rapidly to meet changing performance requirements from AI loads, as well as requirements from grid operators like BESS, UPS, ESTATCOM. So at scale testing, like just what we talked about, can de-risk these technologies and also improve confidence in their EMT models or PSSC models for running grid reliability studies. So as a next step, I think the missing link is developing standardized performance requirements and testing protocols. Right now, we are seeing many of these grid requirements, and we are developing our own testing protocols. But to increase the speed of data center interconnection, we'll need to have a cohesive requirements for testing this power supply equipment. Thank you.
Thanks, Rob and Shahil for the joint presentation showing NLR's testing capabilities and some examples. Now I'm going to introduce Arman Ghasaei. He is the CTO of ETP, EdgeTune Power. He's leading the company testing activities, including the real-time simulation and the controller hardware in the loop of testing the power system management for the data center load. And in his presentation, he will talk about the importance of the real-time simulation and the CHI testing of the power system energy management system. Let's welcome Arman for the presentation. Yeah.
Thank you so much. So hopefully my voice is clear. So should I press? Perfect. So I'm trying to make a quite different presentation, talking about our experience so far. But for those of you who have not heard about EdgeTune Power, we are a Canadian company who's offering consultation and simulation services for our data center clients. But as you can see in the picture, we also build complete power management system for data centers as well. The picture that you see over there is a project we have with our client in Middle East. And our approach is to offer control systems which are well tested in advance over hardware in the loop testing. So that's why you see the title is importance of real-time simulation and hardware in the loop testing for de-risking operation of data centers. So what I'm going to talk about, starting with the problem statement. What's the problem with data center projects that we really emphasize on real-time simulation and hardware in the loop testing? Then what is hardware in the loop testing? What we mean by that? And which devices can be tested in the hardware in the loop approach, particularly for data center applications? And last but not least, I'm going to talk about some results and lessons learned that we had from our 20 megawatt data center project where we offered the power management system for our clients. So I love this picture because it perfectly talks about the problem. So this is an event that happened in 2024, where back in 2024, 80% of people in the utility space or even in power system space, maybe 90% of people didn't know what is large load. And back in that time, so is this the point? If I want to, should I press this one? Or? Yep. Oh, that was. Oh, sorry. So what happened in this event was that there was a very conventional fault happening at the 230 kilovolt feeder, a very conventional fault that you've probably seen on a monthly basis. But it was connected to a 1.5 gigawatt large load data center facility. And back in 2024, nobody knew what is really large load. But as you see, the utility cleared the fault. The data center facility wanted to reconnect. But the data center facility was like, I don't want to reconnect. I think you are not stable enough for me to reconnect to the utility. And the utility got surprised because the utility was like, no, you have to reconnect because I am losing 1.5 gigawatt load, which can result in instability of operation of my system. So I said, please reconnect. And the load was like, no, I don't want to reconnect again. I feel there is a small voltage disturbance at the point of interconnection. And this story happened again and again and again. So as you can see on the picture over there, we have almost 6 attempts of reclosure of the large load to the facility, which is showing that the problem can start from control, it can go to protection, it can go to lack of control and protection coordination for data centers. So sky is the limit. I can like open can of worms and talking about like which aspect of data centers we want to talk about. But the reason I put this picture here is to show that control, protection, coordination between them, proper dispatch of the generation facility in the data center like system, each of them going to matter for proper operation of these facilities and interconnection to the utility. So now I hope I was able to set the stage a little bit on the problem, but let me like do a backward looking approach right now. Even for IBR plants, you all heard about the, oh my God, it's going to take me forever to learn how to work with this. Perfect. So you're going to see, you all heard about the Odessa event, right? 2021 and 2022. There was, again, another type of fault on the utility, and there was 1.1 gigawatt unintentional curtailment of solar in 2021, and 1.7 gigawatt unintentional curtailment of solar again. So question is, they for sure did the PSCAD study, they did like the PSSC study. What was missing? Why, despite all those like studies, they had this unintentional behavior? These are like root cause analysis of why those events happen. And if you look at the table here, we have PLL loss of synchronism, which is a highly nonlinear behavior. We have inverter AC over voltage. We have momentary cessation. Because of time limitation, I'm not going to go through all the details. But these are events that cannot be properly captured in PSCAD. And that is why we want to gradually go to hardware in the loop testing, why hardware in the loop testing can be very, very helpful here. Another point I want to emphasize, and you're probably going to hear a lot from me in the next 9 minutes talking about communication latency, is that in PSCAD or in those like offline, again, I'm not here to like say hardware in the loop is better, PSCAD is good or bad. I look at PSCAD, PSSC as a necessary condition, but as a sufficient condition to make sure you capture all these communication latencies and discrepancies in the controller. You have to again look at hardware in the loop testing. And I put this picture here intentionally to say that in any offline simulation package, you can also put a delay block to like impose 50 millisecond or 100 millisecond. But the problem is that in the actual project, you don't know what is the amount of the communication latency because it can be any different protocol or it can be a combination of different communication protocols in the actual data center project. And here again, I'm talking about IBR plants. There is no Amazon, Google, or Meta who's going to sue you if you cannot feed power to them 24/7 because they're looking for 5 nines, as we all know, right? So that's where we get to the topic of hardware in the loop testing. So hardware in the loop testing is where the name is self-explanatory. You have a loop between a controller and some real-time simulators. And I put all these famous brands over there to imply that I'm not non-biased here. I don't want to say which one is better. The purpose is to show that this methodology of hardware in the loop testing is important, where you can connect the controller to the real-time simulator. For example, if it's an inverter-based like controller, you can send analog voltage or current signals to the real-time simulator and the switching pulses back to the control system of the inverter, which is under test. But for data center projects, if you want to make sure you're doing a comprehensive hardware in the loop testing, you should look at something like this, which is actually the project that I talked about, which we were involved in. So we had a 20 megawatt data center project. We were working with the utility in the client's utility, which is Oman, OETC, which is the Oman Electricity Utility Company. And we modeled the data center facility in the real-time simulator that you can see here. And we connected this real-time simulator not only to the controller of the PCS, and I think you all are familiar with power conversion system, or inverter or battery converter, but also we tested the protection and the meter, the physical protection and the meter. We tested also our complete solution, which was a complete data center, power management system, power plant controller, and an energy management system. And you're going to see lots of arrows here with different colors. What I want to imply with these arrows is that we are testing multiple devices here to minimize time, cost, and risk of commissioning of this project. For example, we are sending firing pulses to the PCS controller is sending firing pulses through digital inputs to the real-time simulator. The real-time simulator is sending voltage and current as analog output back to the PCS controller. We tested the protection. Why? I tried to create a problem in the first slide, because if you do not have PNC coordination between the controller and the protection, no matter how good is your controller protection, if it's going to trip too early, you cannot fully utilize your system for your client. And we also tested the meter. The reason is that, so these pictures are very, very familiar to all of you. These are Schweitzer devices, right? They have IEEE C37 synchrophasor communication protocol, which is a very fast protocol. But if you want to represent that protocol, the simulator itself cannot do that. And you have to have this meter to represent the synchrophasor between the meter and the high-level management system of the data center. So you see we have multiple devices under test. I have to speed up a little bit here. So if I want to further shed light on the difference of offline simulation and real-time hardware in the loop testing, let's say you have the model of your data center and you have your controller protection scheme which should be under test. In offline simulation, when you exchange information between your simulation environment and the control system, time freezes, right? Because you want to exchange information between them. But in reality, that's not the case. Otherwise, I would age less. So you cannot freeze the time, unfortunately. So when you have exchange data between the real-time simulator and the devices that are under test, everything is real-time. You cannot stop the clock from ticking, right? So here is another representation of the difference. In reality, when I send measurements from my real-time simulator to the device under test, clock gonna tick until it sends the command back. So I have this much latency. But in offline simulation, because I can stop the simulation from running, I get back to my simulation at the same time instant that I was sending data to the control system. Oh my God, I have 3 minutes. Okay, so this is a picture of our data center testbed that we developed in-house. And as you can see, we are working with very good OEMs right now. And the purpose is to have their control system in our laboratory. So we make sure for our clients, we do high fidelity testings. We have genset, we have battery systems, as you can see. We have models of different NVIDIA GPUs like A100, H100, GB200. And this is a picture of our real-time simulation laboratory. I'm going to pass this one. This is a model of the client that we worked with in Oman, and we are still working with them. So it's a 20 megawatt data center facility. So what we have between the utility and our power management system, we even were able to represent I would say old communication protocols like IEC 104. But the utility was this is the communication protocol that I want to go with, and you have to represent it. And we were able to successfully represent that in our test bed. And also, as you can see, we have like model of the UPS system, we have like the GPUs, and we have like a central battery system, and also battery system which is supplying the DC side of the UPS. This is a picture of the data center controller. I'm gonna probably pass this point here. But this one is like maybe a picture I can show here. So again, why hardware in the loop testing? We were testing the PCS for that project. So my apologies if I redacted this part because of the NDA, so I cannot say who was the OEM for that project. But we wanted to test a transition from grid forming to grid following for that PCS. When we were testing the physical controller, we noticed these jitterings. We call it jittering. Like when you want to switch from GFM to GFL, that was the problem. Believe it or not, the OEM first denied, and then they said, can you put a cap bank on this terminal here so we can solve the issue? So that's something that you cannot observe in offline simulation because you have like a model developed of their control system. We have 40 seconds. Okay. So I'm going to probably bypass this one. We did also some accidental, unintentional islanding of the facility, which was a very important testing for the data center project. And we showed compliance with IEEE 1547. IEEE 2800 is the norm in like North America, but IEEE 1547 and 2800, they're talking about voltage and frequency. It's just at the transmission and distribution level. Last one, great, I have 3 seconds. So they also had the issue of subsynchronous torsional impact between the gensets in the facility and also the AI loads. And we just have our patent pending IT SSO 555, which is a generator-centric solution because you don't need 100 megawatt battery if you want to damp oscillations or torsional impacts on a 100 megawatt genset. You can have a dedicated battery for the generator. And with this solution, we were able to help our client. So as you can see on this plot here, with our solution, we were able to effectively damp the subsynchronous torsional impact on the generator on different load profiles with different amplitudes and frequencies of oscillation. Sorry if I talked too fast. I had no other choice, and hope you enjoyed the presentation. Thank you.
Thanks, Arman, for the very interesting presentation showing the importance of the HI testing, which is a different flavor of the EMT and the hardware testing. And now we're going to introduce the next speaker, Wook. Sun is a senior manager on the grid stability study team from ERCOT. He's supporting load and generation interconnections as well as system planning studies. Please join me to welcome Sun. Yeah, please take it away.
So good afternoon. Thanks for giving me the opportunity to share ERCOT practice for large load modeling requirements and model quality test. Before I get to the detail, let me give you a quick high-level overview. I think Eric kind of covered this morning, but the chart really is from our generation. I mean, large load interconnection queue. Currently, we have more than 400 gigawatts of large load projects. They're all seeking a transmission interconnection. They're not traditional industrial load. As mentioned by Eric this morning, more than close to 90% of them are data centers or crypto mining load. Their size is not small. Some of the individual load is huge, 1 gigawatts or 2 gigawatts. And they are packed with power electronics components and similar to IBR. They are very sensitive to some system disturbances, particularly in a weak grid condition. So we have a lot of concern. So imagine that tens of gigawatts of large load data centers, right, sitting in the weak grid region and tripping all at the same time without riding through the fault, right? It can be a huge challenge to our system operations to manage. So it's not an imaginary situation here. We have observed, a number of load loss events for the last several years. So far, we could handle it. Our system operations could manage this, but as we continue interconnect those large data center load, it's going to be more challenging, and the loss impact will be bigger and bigger, right? So we are making an effort to address those challenges, but to evaluate those, load loss impacts, we need to have a good model, right? Everybody wants to grab the model and do the interconnection study and system planning studies and so on. But we all know that the traditional composite load model, has some limitation and is not suitable to represent the nonlinear characteristics of the data center load, right? And that's why, ERCOT, working with industry and participating in, the reviewing and testing some of the user-defined models, which is currently available in the NUG NMWG website. Right? And we believe that that's the best model as of today. But for ERCOT accept both genetic, standard library model or user-defined model as long as it accurately, reasonably represent the dynamics of the large load. Okay? We also recommend our load customers to better represent their cooling and power electronics portion of the load there. We recommend them to split the load into two, cooling using a CMLD model if that's sufficient, or power electronics portion of the load using a UDM model. So that's the currently that we are making an effort to when we get the models from the large load customers. And it's not just a modeling issue, but also it's a issue from the transmission service providers. Some of the TSPs not familiar with these new types of load. They wonder what kind of questions need to ask and what kind of data need to be collected from those data centers and crypto miners. So ERCOT and our dynamic working group TSPs work together to develop a large load data survey document. It consists of about 69 questions ranging from fundamental information all the way to protection settings and voltage ride-through characteristics. We are currently in transition, moving from version 35 of PSSC to version 36. We are aware that there is a better model, the standard library model in version 36, but we're also aware that there's some issue with that model. There's some area to further improve. So we need to work together with industry. So to address all those, ride-through issue and load loss issue, we are making some, two complementary efforts, right, to establish some rules and requirements. So NOGA 282, Nodal Operating Guide Revision Request 282, that's been proposed and submitted. I think it was approved by the board of directors early June. It's getting close, but it basically defines the voltages and frequency ride-through performance requirements for all large computational load. In parallel, we also proposed Planning Guide Revision Request 144. It basically clarifies what kind of data need to be submitted and also model review process throughout the interconnection. So I will talk a little bit more about those two. I'm not going to talk about the details on Nova 282, but here's the summary of voltage write-through requirements outlined in the Nova 282. On the left, you see voltage bandwidth and corresponding, minimum write-through durations. So they have to write through the fault within that, requirements. And on the right, we have some key performance indicators. And some of the things that I can say is they have to continue consume power, during the low voltage dip and also high voltage conditions. And once the voltage is recovered after fault is clear, they have to come back to the grid within the 2 seconds. Okay, so again, this Nova 282 is available in the public website, so you can go ahead and take a look at it for more detail. Figure 144 has 3 key components there. 1, data requirements, and 2, model quality tests. So it introduced the model quality test to ensure that the large computational load meet the performance requirements, the voltage write-through requirements that's proposed in the Nova 282. And it also defines the key milestones for model checking, right? They have to go through, model checking process at certain, the milestones throughout the interconnection process. This Figure 144 also establish a review process for potential modifications to the existing operational large computational load. In case they have some changes, they have to come back and go through this review process for ERCOT approval. Of course, we require accurate model. There is no negotiation on this one. But when they submit the model should be compatible with software platform, as described in the DWG Dynamic Working Group Procedure Manual. We have 3 software here: PSSE, PSCAD, and TSAT. TSAT is being used by our system operations for real-time TSAT analysis. PSSE is traditional dynamic stability analysis tool being used in the connection study. PSCAD provide very high fidelity EMT analysis that can capture sub-cycle phenomenon that cannot be evaluated in the PSSE or TSAT. And model quality test has to be done using all 3 softwares. That provides very important cross-model validation step. For example, you can make sure that your PSSE model is in good shape by comparing the response of the PSSE model against the response from the PSCAD model. And so that's one of the important steps in the model quality test. So MQT framework. So we have created a separate sections in the Plan Guide Section 6 to describe the model quality test. Is very similar to the model quality test for IBR, but it's much more simplified version. It has a site-specific MQT and also converter model validation test. Site-specific MQT, consists of flash start test and a large voltage disturbance test. You should not move if there's no system disturbances, it should be flat. And for the large voltage disturbance test, they can test the voltage write-through, test curve to demonstrate they meet the performance requirements. Okay. Again, the MQT must be performed using all those 3 software, and converter model validation test is only for large computational loads, so data centers and crypto mining load. It's a hardware benchmarking test to ensure the PSCAD model of the converters is matching with the actual response from the actual hardware converters. Okay. It has 2 tests: large voltage disturbance test, which I mentioned just earlier, and has also a subsynchronous test. Subsynchronous test is about performing frequency scan sweep to make sure that the PSK model of the converter is in good shape, not only for nominal frequency, but also for other range of frequencies. Right? And as far as performance requirements, all large computational load must meet the performance requirements in the Nodal Operating Guide, section 215, which was proposed in the NOVA 282. But non-LCL, so other traditional load, they are required to submit a model quality test, but they are not required to meet the performance requirements. Okay. And this is the ERCOT recommended large load voltage ride-through test curve. It is essentially designed to test that for the performance of the large computational load that need to meet the criteria in the NOVA 282, but also to check and understand the ride-through characteristics of other larger load that are not required to meet the performance, the requirements in the NOVA 282. It starts with a flat start, and then going down to a voltage ramp down test, which applies the gradual, moderate voltage variations before initiating a sudden voltage dip, like a shallow fault and default, which is followed by high voltage condition. At the bottom is an example of acceptable load real power response. As you can see, they ride through and they continue consume power even at the low voltage conditions. And after default, right after voltage is recovered, voltage clear, voltage recovered, and the load coming back, within 2 seconds. And on the high voltage condition, it continue consume power at the pre-disturbance level. I think one of the speakers talked about the hardware in the loop test. So I will just make it quick here. So for the converter model validation test for large computational load, ERCOT has been accepting the hardware in the loop test. Okay? It can be done in the OEM environments and can be done only once for the specific converter or family converter. These are the key milestones for the dynamic model review in the interconnection process. We have 3 key official model checkpoints, right? But regardless, we require a large load customer to submit their model update whenever there is change, so we can take a look at it. Right? But these are the key milestones. Okay, so one, before stability study, they have to demonstrate they meet the voltage ride-through performance requirements before they getting into a stability study, and then before the quarterly stability assessment, they have to submit the model quality test and all 3 different models in different software platform. Quarterly stability study is a cluster study that incorporates all the generations and larger load that are expected to be in service in the next several months. We put everything together to understand the system impact, to come up with any mitigation plan or operation limit. Right? But that to enter into that QSA, they have to submit all those necessary information for review. And for large computational load only, they have to go through one final round of model review process before initial energization. They have to submit as studied data, which was assumed in the QSA, and they also submit the as-built data, right? We can put as many as model checking point in the interconnection process, but we believe these 3 model checking point is good enough. But the whole point we're doing this is to help our large load customers and our TSPs to maintain the model data and model performance throughout the interconnection process. One thing that I want to point out is this model quality test review. The primary purpose is to ensure they are in good shape to move on to the next step in the interconnection process. This is the minimum test and review and it does not guarantee, or ERCOT does not endorse that they will meet these requirements in the real-time operations. It's their responsibility to meet the operating requirements. And I've seen, many large load coming behind the existing generation resources. Then they have to go through a lot more rigorous review process. They have to go through large load interconnection process, but also they have to go through generation connection process. And as one big family, the generation connection process, during that process, they have to work with the resource entity to provide a different level of model quality test for the entire generation resources. Okay. So a lot more rigorous review going on if they are co-located with existing or new generations. So key takeaway, ERCOT's been making a huge effort, right, to address all those challenges and ride through capability issues. I think one thing that I just want to mention before I wrap up, we are in the learning process, right? We set up some rules, but as we continue learn more and more, we can come back and refine these rules and requirements. So we need to continue work with our industry to improve the modeling approach and also reliability framework. So that's all I have. Thank you.
Thanks, Wook, sharing the across experience in the model requirement and the model quality test. I've noticed a lot of data center related stuff is borrowed from IBR. Yeah, that's great to learn that IBR set up a foundation, so that will be helpful for data center load related studies. Yeah. Now we are moving to the last presenter, Suman Samarakoman. Suman is with Electronics Corporation since 2019. Prior to that, he was with Manitoba Hydro International (MHI), which TS card. He has more than 15 years experience of doing the power system stability study and analysis. He will talk about the EMT testing of the large load power fluctuation. Let's welcome Kusum for his presentation.
Thank you. Hopefully you can hold it for another half an hour. I got 15 minutes though. My name is Kasun Samravikram from Electronics Corporation based in Winnipeg, Manitoba. So if you heard about Electronics, we're a small consultancy firm based in Winnipeg, mainly doing EMT studies, strong background in PSCAD. Our founder is Dennis Woodford, who wrote PSCAD at the first place in 1978. And we have a group of engineers basically doing pretty much PSCAD is our bread and butter. So let's start with that. So I think my team here is pretty much gave the background for the why we need these large load fluctuations mitigations. So I can probably skip my first 3 slides. So let's jump into all the way right here, and then I'll start from here. So this is the problem. So we already discussed this one. So when we have large loads, we have power fluctuations. So if we don't mitigate these power fluctuations, we will have these problems in our generator shafts, and we will have problems in the frequency flicker everywhere. So I think it's not a question anymore. We need to mitigate this. So so what are the key modeling aspects of mitigation studies? So first of all, if you want to mitigate, we need to have something to mitigate against. So we need to have a requirement, right? So otherwise, without a target, we cannot mitigate. So let's say whether it's a 10 megawatt or 20 megawatt, whatever the number is, we need that number published. Then we can have a process developed to mitigate to up to that number. So supplementary devices with energy storage is required. So in other terms, when we have this power fluctuation, the power goes up and down. So you need to fill that gap with something. So when you fill that gap, you need energy storage. So energy storage could be batteries or supercapacitors, or any form of energy storage. You need something that can store energy and then discharge into the grid or absorb such a way that you can flatten out that power curve that we have these fluctuations. So the load profiles, including the load shapes and ramp rates, are very important and we have to select carefully in these mitigation studies. In other terms, you can select a load profile that pass the requirement and that fail the requirement as well. So what we should select? Wrong answers only, right? So none of them are right. So we need to select a load profile that is realistic. So it's not which is passing or which is not failing. So what is realistic? I'll talk about a little bit in the next couple of slides, how we're going to select this load profile and what kind of methods that we can use to mitigate these load fluctuations. The real code models of these units. So in other terms, if you look at a data center, we have a bunch of different categories. We have cooling loads and all sort of these. And then we have on top of that is a major part is the IT load, which could be 70%, 60%, whatever that number is. That is the main part that we are trying to mitigate because that is the load which is fluctuating drastically. So for that to simulate in a correct way, we need the power supply models or the UPS models model right. In other terms, we need the real code models. This is going a little bit, the Shahils and Brett talk about the generic models. Now I'm basically trying to convince those are useless. So in other terms, not in a good way. So these models, as Shahil mentioned in previous presentation, those are essentially the bridging the gap until we get the real code model. So that is very important. We need to have something until we have the correct model. So the real code model is important. That is kind of our ultimate goal is to, and we can discuss a little bit of why we need these models to evaluate these mitigation levels. And an EMT model, a relatively small EMT model is required, so you don't need a big wide area PSCAD model to do these studies. Pretty much like a model quality test, MQD testing, like a SMIB model. You can use that kind of a model for the mitigation studies. And the system strength is important. What are the SCR and XOR values that you use? Because that will have the impact based on the type of the mitigation method you use. If you use a GFM batteries, that the grid strength matters because your initial phase jump power depends on how much of your grid strength is. So these are the few mitigation options that we have studied, and maybe this list is growing. At least for now, these are some of the mitigation methods available. We have tested, except the last one. Pretty much I don't know much about, I just put it there because everyone's talking about it. So the first one is a GFM BESS. So everyone knows this is a GFM BESS is uncontrolled mitigation kind of method. You don't need to have an active measurement. You just connect it, and then based on the phase jump, you'll compensate power automatically. It's a kind of a physics based. It's not an active controller. And then we have a second type, a BESS with active controller compensation, which is you actively measure the power fluctuations and inject the reverse of it or the opposite polarity to make it flatten out. So that is I don't have a name for that, so I put the BESS with active power load compensation functionality. And the third one is the eStatCom. So that is another a device that actively compensates load using supercapacitors. And a fourth one is a combined solution, which is a eStatCom together with a GFM BESS, which is typically required for a eStatCom, because eStatCom supercapacitors are, the energy storage is in second levels. It's not in minutes level. So if you have a low frequency load oscillation, you probably need a additional compensation on top of the eStatCom, which is why I put the number 4 as the eStatCom plus the GFM BESS. And then we got 3 double conversion UPS types mitigation methods. One is the low voltage one. which is kind of the industry established method for typical UPSs, online double conversion UPS. And the second one is the online double conversion UPS, same UPS with a GFM battery, because these the low voltage double conversion UPSs are again low energy mitigation method, so you need some kind of a supplementary power. And the seventh one is the double conversion UPS medium voltage, which inherently has a large energy storage, so you don't need a separate battery or energy storage on top of that. And the last one is the GPU level mitigation. Probably Scott gonna talk about, hopefully will talk about it. Don't know much about that. So critical factors in EMP modeling. So there are two categories we can categorize these mitigation methods. One is actively measure and inject power. The other one is kind of the physics-based, so the impedance-based methods that automatically inject power based on the phase angle jumps. So in the active compensation methods, which are actively measuring the power and inject the reverse power injections, those are very important. There are a few important factors need to be careful in these models, especially the communication delays, measurement delays, processing delays, and filtering and sampling. Because if you change these delays by even a 1 millisecond, your efficiency can be dropped drastically, and you might not pass or not fail change. So these communication delays, as Arman mentioned in his presentation, is kind of the values that we put is a guess value, or it's not a very a value that we can say 100% this going to be the worst case value. In other terms, we can put a communication delay as a value that is kind of the worst case. We know the actual one we will be faster than that, then we are good. We are going the good side there. So otherwise, if you try to calculate a communication delay which is not 100% right, and then try to kind of play with these delays, is kind of dangerous, because we can make a situation which is pass or fail based on these delays. So this applies to pretty much all these, the eStatCom and the battery with active power compensation functionality. The closed loop response time, in other terms, need to be accurately modeled, or need to check with the manufacturers how these are modeled to have the proper performance. And the passive devices, as an example, double conversion ones and the GFM batteries, those ones, what are mainly important is the impedances model right. So if you have your grid impedances and the plant transformer impedances, especially the last two bullets, is the battery internal impedances and the lead impedances. These two are also very important in a situation where you have a double conversion UPS. Your battery impedances and lead impedances will make your DC bus voltage not flat. If you in a typical BESS setup that we have seen, we usually model the DC bus as a DC voltage source, pretty much ideal voltage source or some impedance. So essentially, your DC bus voltage doesn't move at all. So that will decouple to the grid side, to the load side. But if you have actual impedances, that your DC bus voltage will slightly change, and then that will show up in the AC side as a ripple as well. So those impedances are important to model when you modeling a passive mitigation devices. And monitoring is also a very important thing. So if you work with PSCAD, you probably know that these multimeters, PSCAD multimeters, you can measure the active power. That is instantaneous active power. When you say instantaneous active power, is essentially it's calculated using VAIA plus VBIB plus VCIC. That is the equation for the instantaneous active powers. There's no filtering should be applied. You can apply some filtering for the very high frequencies. So the typical smoothing constant on these numbers in these meters are usually 20 milliseconds. If you use a 20 millisecond real pole kind of a filtering on instantaneous power, what you're essentially doing is you're cutting out any frequencies about 8 hertz. So that number is too big, so you need to use a very small filtering, probably around 1 millisecond. That will make sure you are only filtering out very high frequencies, not filtering out the components that we are interested at. So this is an important one. So what really matters in the mitigation method, what really affects the efficiency of a mitigation method is the load ramp rate. So you can ramp a load in a step way, that it means instantaneous kind of a rock-off, or sorry, instantaneous step as the power, or you can do in a kind of a second order function, this kind of a picture in my screen. What is realistic? So because you can make this load ramp in a different ramp rates, such a way that you will have some residue power left at the grid side, which can pass or which can fail. So the important ones is you have to, that's where this is the place where your real code UPS models comes into the picture. You can change your load at the DC level or the GPU level as a step, but it'll show up in the medium voltage level as a ramp or some kind of this type of a function. In certain cases, if you look at a single phase power supply units, like those are typically, if you use a real code model, you might see your load change 100 megawatt, but high side of the power supply might change 120 megawatt. You have overshoot there. So essentially, you need to mitigate more than the load change in certain cases. So those things need to be captured properly. That's where the real code model important comes from. So this is a typical waveform that you can, this is not from a simulation. This is just, even though this looks like a PSCAD, it is PSCAD. I just mimic such a way that to protect the non-disclosure agreement. So this is not from a real simulation. So this is if you look at the load profile, so you can think about like a step load profile, like a square wave. And then after the UPS, so power supply, you can see a little bit of a ramp or kind of a shape applied into those vertical lines. And then injection from mitigation device is the third one. Very similar to the first one, but there is a difference between those two. It's not visible in this one. The one in the bottom is essentially the second one minus third one. So the gap between those two is the red one. So the red one, you can see the peak to peak, there is a value left. So this is the value that the grid requirement is looking at. So this value need to be lower than certain value, the peak to peak number, let's say 10 megawatt, 20 megawatt. So that's very important number to look at. So let's go to my final slide. So this is kind of the $1 million slide I have. So this is a summary of results from a bunch of studies that we have done, and then kind of a quantitative numbers I converted into qualitative format in that I can present here. So there's a lot of detail in this slide, so I might run out of time, already 4 seconds left. So I'll try to give a little bit of a high-level picture rather than going one by one. So in the active power, active measurement-based mitigation methods, so you can see that for the load compensation efficiency, last two rows, last two columns, if you pay attention to the last two columns, is essentially the efficiency of the mitigation method. So you can say it's a low to medium, and if you have a best with some kind of active power measurement-based compensation, you have slightly higher compensation. So you can see the ESTATCOM plus ESTATCOM plus best combinations will have even better compensation accuracy and the compensation efficiency. And all the double conversions pretty much have better response or better compensation efficiency in general. And also those has pros and cons as well. If you look at the loss column, so you have double conversions will have higher losses because you have two back-to-back converters. Another one is your entire power need to go through these double conversion unit as versus to the shunt devices. You need only the varying part of the power is the only one need to go, or the sizing need to be considered. So in other terms, do we need the fully flat or always the 100% compensation? Maybe not, because we have a requirement. Let's pick a number, let's say 10 megawatt. So if your data center is like 1,000 megawatt, you need to meet 10 megawatt, then you need a better efficiency that you need like 0.1% compensation, right? And if you look at if you have 200 megawatt data center, probably you don't need that. You can get away with a GFM base or a EastEdCom plus best kind of a solution. So it doesn't not mean better is always required, but we need to based on your size, because all these grid requirements are not per unit based requirement. Those are hard code numbers. 10 megawatt, 20 megawatt. Doesn't matter your data center is 500 megawatt or 1,000 megawatt. You still need to comply 10 megawatt. So that's where the spread comes from. This is you can pick basically based on your requirement. Thank you very much.